Why is inductive reactance different from resistance? Imagine trying to push a swing. Resistance is like pushing against a steady force that slows you down equally no matter how fast you go. Inductive reactance is more like trying to push a swing that resists sudden pushes but responds differently depending on how fast you try to push it. Resistance is caused by collisions between electrons and atoms inside a material. These collisions convert electrical energy into heat. Resistance always opposes current flow equally, whether the current is steady or changing. It makes voltage and current stay in sync, so they rise and fall together. Resistance does not change with frequency. A resistor with 10 ohms of resistance will oppose current the same way at 50 Hz or 500 Hz. Inductive reactance only appears in circuits with inductors, which are coils of wire. It opposes changes in current, not the current itself. When current flows through an inductor, a magnetic field builds around the coil. If the current tries to change quickly, the magnetic field resists that change. It temporarily stores energy in the magnetic field and then releases it back into the circuit. The faster the current tries to change, the stronger the magnetic field's opposition. That's why inductive reactance increases with frequency. The formula for inductive reactance is 2 times pi times frequency times inductance, which tells us how much the coil resists changes at different frequencies. Another key difference is how voltage and current relate in each case. In a resistor, voltage and current are in phase, meaning they reach their peaks at the same time. But in an inductor, the voltage leads the current by 90 degrees. This phase shift means the maximum voltage occurs before the maximum current. This phase difference is a clear sign of reactance and does not happen with pure resistance. Energy behaves differently too. Resistance always turns electrical energy into heat, so energy is lost. Inductive reactance, however, only temporarily stores energy in the magnetic field. Over a complete cycle, no net energy is lost in an ideal inductor. The energy just moves back and forth between the magnetic field and the circuit. When both resistance and inductive reactance are present, they combine into what is called impedance. Impedance is the total opposition to current flow in an AC circuit. It is calculated using the Pythagorean theorem, combining resistance and reactance as perpendicular effects. To sum up, resistance opposes current uniformly, turns electrical energy into heat, and keeps voltage and current in step. Inductive reactance opposes rapid changes in current, stores energy in a magnetic field, causes a phase shift between voltage and current, and depends on the frequency of the AC signal. Understanding these differences helps engineers design and troubleshoot circuits that use inductors and capacitors, which are fundamental in electromagnetism and fields within electrical engineering.